So thanks for inviting me. Yeah, I'm actually an NCASS scientist, National Centre for Atmospheric Science, but I'm based at the Met Office Hadley Centre. I'm going to tell you a little bit today about where we are in developing the second UK Earth system model, but also its precursor, its physical core, which is based on HADGEM-3, GC5, GC standing for Global Coupled Configuration. I think many of you know the HADGEM acronyms. And one reason we're developing these models, not the only reason, but one is for CMIP7. And generally we release the models for community use as well in the UK and by unified model partners in different parts of the world, including Australia. So thanks to a number of people at the Met Office and then the NERC teams and for contributions to this talk, particularly the 4 that are listed there. Okay, so just some background first before I get into details. So as was mentioned, UKSM development is a collaboration between the Met Office and NERC. It does involve a number of external partners as well from the UK, including people from Australia somewhat. I mean, you use the same atmosphere, at least, or physical atmosphere. And I think you use a variant of UKCA as well, the chemistry and aerosol scheme. And then there's also people from New Zealand and Korea that are involved too. The timescale for our development of the Earth system model is roughly, we've been working on it, give or take a year. And I think it won't be till early 2026 that we have something fully ready and working. That's a bit later than we originally planned. And this talk hopefully will indicate why that is the case. I'm just going to put a timer on myself. So we're assuming, based on CMIP guidelines and things that are coming out at the moment, and we in the UK yesterday actually had a first sort of planning meeting for CMIP7, I should say, déjà vu, getting the community together here. So our understanding at the moment is there's likely to be 2 timescales for CMIP7, one that's being referred to as a sort of fast track activity that hopefully feeds sensibly into the IPCC timelines when they're known, and one that might be on a longer timescale, which is more oriented around scientific as opposed to, let's call them, policy relevant activities. So we hopefully have the model for both setups, but you can see there is now a difference in our timelines. So it may well be that we need to have a backup option for the fast track, and I'll mention that as well. So just to say, the UK Earth system model is based on the physical core, HADGEM-3 GC5, which is the last unified model-based GC model before moving to the new ELFRIC/Momentum/NGMS-based system. One word to say is that the typical approach for both the global atmosphere, which in this case is called GAL9, and the global ocean, which is based on NEMO, which is called GOSI9. The basic approach for those models and the coupled model is what we call an emergent approach. What does that mean? It means there's actually no coupled transient climate change experiments involved in the development of the model. So it's very much a bottom-up approach. So the historical evolution, the effective climate sensitivity, and the transient climate response are emergent model properties or surprises. Should also say that the main development was done at a resolution of N216 in the atmosphere and 1/4 degree in the ocean, and higher resolution atmospheres that are used for global forecasting. So N640, for example, in the atmosphere. For the Earth system model, we will carry on with N96 Orca 1. N96 is about 135 kilometers in the atmosphere, 1 degree in the ocean. And there was need, and there is need for further tuning, because this time around, the global radiation budget at the top of the atmosphere is quite sensitive to resolution, which wasn't the case before. And one point I'll come to as I go along, there was a decision taken early in the process that we would have a development also of what we're going to call a more effective climate sensitivity central GC5 model as an if needed. We'll use a PPE, a perturbed parameter approach in the atmosphere mainly to try and develop something that's more mid-range within the context of the IPCC WCRP estimates of effective climate sensitivity. And I'll come back to that. So GC5 was released a while ago now, November 2022. There was an assessment workshop that some of you would have been involved in. On the right are the changes listed in terms of the atmosphere. I'll just put a pointer on. In terms of the atmosphere and the ocean. And just a very summary slide. So this is on the left is a root mean square error map, where it's a % change in the spatial root mean square error for present day climate statistics in GAL9, comparing over 2 resolutions, blue N96, red N216, GAL9 against its predecessor GA8 and GL9, so GA8 in the atmosphere primarily. And negative numbers means that GAL9, the latest atmospheric configuration, performs better for present day than the earlier configuration for a basket of different metrics. And then there's a plot here on the lower panel showing the Drake Passage transport in the ocean. This is actually just an ocean model simulation, but the basic message holds for the coupled model as well. Dashed lines are GO6, which was the ocean model used in CMIP 6, and the full lines are the GOSI9. Going from red is 1 degree, dark blue is a 1/4 of a degree, and light blue is a 1/12 of a degree. So in particular, you'll see for the 1/4 of a degree, there's an improvement in that we had a very weak ACC transport at a 1/4 of a degree, and that's improved quite a bit, but it's still low relative to observations, which are on the right here, this bar. The 1/12 of a degree improves things further, and actually the Oka 1 for at least the ACC transport, at least the mean transport, is an improvement and relatively good. Okay, there's a long list here of things that are claimed to be better, and this is from primarily the model developers at the Met Office, not me, for GAL9 and GC5, and I'll let you read those. The key point, I think, is that the GC5 development isn't solely for climate or climate change experiments, it's also for global NWP, it's for seasonal prediction, and it's for decadal forecasting as well. So we are one of the users, a relatively important one, but nevertheless still one of the users. I'll push on for the sake of time. So the model was performing well, it appeared, for the present day. And then we decide to run on the left an abrupt 4 times CO2 experiment to get the climate sensitivity. And on the right, 4 historical members using CMIP 6 forcing. And hey presto, this good model for the present day gives an extremely high climate sensitivity. So the WCRP likely range, I believe, likely range is 2.5 to 4.5 Kelvin. So this is definitely outside the expected range, or the accepted range, let's say, for climate sensitivities. And you can see that's manifested in the historical simulation, in that there's a very, very strong warming post about 1975, 1980. Earlier, green is observations, I should say. Full black is the ensemble mean of the 4 members, which are the light grey lines behind. So pre sort of 1975, there's relatively good simulation of the global mean surface temperature record. I haven't got it here, but the north-south difference is also rather good and suggests that the aerosol forcing per se is probably okay. And this main driver of warming is probably a CO2 induced response. So I'll push on. So this meant that this PPE option that we had been working on became more and more relevant as we went along. So there was a consultation exercise held by developers of the physical model around the 2020-2021 time period with different users, one being the ESM group, but others being things like the seasonal prediction group, the groups that developed the UK climate predictions, so UKCP. And all of those groups, it came out that the climate sensitivity, the transient climate response, and in particular, the quality of the historical performance, not just the present day time mean performance, were extremely important. This led to these 2 strands of model development, one being the emergent one, and one being what is called for the time being central EFC, or central climate sensitivity. You might think it, when I show you the slides, that it maybe needs a new name, but at the moment it's central. And the idea was to use a perturbed parameter ensemble for the atmosphere to try and get candidates that had a lower climate sensitivity and a more acceptable performance for the historical period. So effectively, climate sensitivity and historical performance becomes part of the model development axis. So the way this was done, this is a figure from David Sexton, who led this work. So what was done is listed here on the left, and the figure gives a summary of the outcomes, and I'll just say what the figure is first. So the lower axis is the feedback parameter from AMIP plus 4K experiments. So AMIP experiments with 4 Kelvin added to the prescribed SST everywhere. And the vertical axis is an aggregate error of a basket of metrics again. So it's the root mean squared error for the AMIP present day simulation. So what was done is there was a PPE and 5-year members of AMIP and AMIP 4 plus K runs were made. 503 different members where a combination of different uncertain parameters in the atmosphere, controlling things like convection, cloud feedback, cloud microphysics, aerosol to cloud, boundary layer mixing, even gravity wave drag, were perturbed. That gave you this blue envelope of an emulation of the 503 members, gave you this blue envelope in the feedback versus error space, with the yellow dots being the actual AMIP runs that were the 5-year runs. And then of those, 41 of them were selected based on their lambda or their feedback parameter to be taken forward into coupled simulation. These are these blue ones, so they're very much on the edge of the GC5 range, but they span this sort of -1.6 to -1.3, which is a stronger negative atmospheric feedback, primarily, but not exclusively governed by cloud feedback. Then those members were run for another 40 years in pre-industrial to look at their balanced state and look at their performance in terms of global mean top of atmosphere radiation. And from that, a single member was selected that was then run further and then was transitioned into historical and 4 times CO2 runs. So we're interested in these purple dots here in this space, and the red dot is the emergent model. So the red dot is the GC5 emergent model, which has a pretty relatively weak feedback compared to these other ones, but also has the lowest or almost the lowest aggregate error for the present climate. So just to cut straight to the chase, if we do these integrations, the effective climate sensitivity for this particular configuration is coming out at 4.8 Kelvin. So it's still relatively high, but it's obviously significantly lower than 6.6 Kelvin. And in terms of historical performance, it's still warming more than the historical record. If I just flash back, you'll see that, hopefully you can see that it's warming less. It is still warming more than the historical record, which may imply other aspects, or it may imply that the ECS, which has a role to play in this warming here, some role to play, is still overestimated. One thing we haven't looked at, and we need to, is the ocean heat uptake in this period, whether the ocean heat uptake is strong enough. I should say that in this work, there has now been a bug identified in the PPE, the original PPE setup, which needs us, it motivates us to rerun these couple of PPEs to make sure that this, and then this as well, to make sure this result truly holds. And that is work in progress. And this central GC5, as it's dubbed at the moment, it's run now for over 500 years in pre-industrial control, and we've deemed the top of atmosphere radiation balance and various aspects of the control climate are drifting too much. So we do need to do some further tuning and to make sure that that doesn't impact our findings in terms of climate sensitivity and historical performance. The next 12 months, are we shifting to in terms of its use for climate activities? CP, there is some additional tuning in the mean climate, the long-term climate, effective climate sensitivity again, of course, and get not abandoned. We will still look at and use the emergent model, but it will be used fairly selectively given its climate sensitivity. Okay, I'll just move on then to a few slides from UKSM2 before stopping and taking questions. So a summary again, the initial development of UKSM2 was using the emergent GC5 model. I'll jump down. Once there is a more stable GC5 central and the UKSM team is involved now in developing that, then we will switch developments to the central model. But at the moment, we'll continue with the emergent model, mainly because the technical development can go ahead. That model does in the PI control give you a relatively stable and okay climate. So a lot of the development can be done around that, but there will be time needed to make the switch as well. In the UKSM development, we aim to, I've put here, maximize Earth system process realism and interactive coupling. That means we view the physical model as, if you like, a safe bet. It may not appear safe from the climate sensitivity. And then the Earth system model we build on top, we want to really emphasize couplings and things that are not in the physical model, and I'll come to those in a minute. One of the things we're trying to do is now prioritize the Earth system model to be emission-driven as opposed to concentration-driven as the standard model, and the concentration-driven model to be the second model. And that means emissions of primarily CO2, but also in our case, we can now run with emissions of methane and a full methane sample. And we will try and aim for both as our standard model. We're keeping the resolution initially at the same as in CMIP6, so that's N96 in the atmosphere, 85 vertical levels that goes into the mesosphere, 75 levels in the ocean, and a 1 degree model. We are developing, and we have been for a while, a hybrid resolution model where we run the atmosphere physics at a higher resolution, dynamics, N216, and the more expensive chemistry and aerosols at N96, and run that interactively. And we're working on the ocean as well now, running the ocean at potentially 1/4 degree, and the ocean biogeochemistry at closer to 1 degree interactively. That's work in progress. So that I've talked about already. The primary development is with the emergent, but we're switching to the central. So now a couple of examples of where we are. So first, what are the new system developments that we're putting on top? The ones highlighted in bold are my take on the bigger ticket ones, but there are a number of developments that are going in. And the color here, green, means they're fairly mature, and we're already doing what we refer to as package testing of them on top of this GC5 emergent. Orange means they're fairly well progressed, and red means they're less mature. So we will run, and we want to do this standardly, to have interactive ice sheet models for both Greenland and Antarctica in the standard model. We do already have that in earlier configurations of the Earth system model, but we didn't run it in CMIP6, for example, as the standard. We will this time around aim to do it as the standard model. We want them to, as I said earlier, to be emission driven both for CO2 and methane. We're working on interactive fire, so having a fire model coupled to atmospheric composition, carbon cycle, so terrestrial carbon uptake, and the dynamic vegetation that we already have. The fire can burn vegetation, vegetation can hopefully respond and recover when fires stopped burning. The other big ticket item that I've highlighted is we're increasing the number of model soil layers and going deeper to support permafrost, and we're confident we'll have the soil layers and the deeper soil layers working, and we're hopeful that there will be also a bit of permafrost biogeochemistry in there as well to connect to the methane cycle. That's less mature, but I think it will get there, particularly now that we've got a longer timeline. There's some smaller things, so the improvements to stratospheric ozone, prognostic nitrate aerosol is pretty much in there, so that's good as well. Thermal acclimation of vegetation, so that's letting photosynthesis be adaptive to slower warming. And then some smaller things in the sort of link between aerosols and the physical atmosphere. So a variable cloud pH, modal dust. So we've always used the BIND classic modal dust scheme. We would like to move over so that it's treated by the GLOMAP modal scheme in the same way that all the other aerosols are. Boundary nucleation of aerosol particles, and a few more things in the ocean and atmosphere that I won't have time to mention today. So one of the things that we're being pushed a little bit by is these plans that are coming together for CMIP7, where there's a suggestion of a fast track set of activities, and then a suggestion that the more sciencey MIPs might be on a slightly slower timescale. If CMIP sticks to the timescale they're suggesting, which past experience says it was going to be a challenge for them as well in terms of forcing and scenario data, then that might suggest we need to have a model ready by sort of mid-2025 or late 2025. And probably we think we wouldn't have a fully spun up UKSM2 on those timescales. So we've come up with what we think is a backup option, and we talked about this yesterday in our community group, and it was considered to be an okay backup option, but okay only, I think was the general feeling. So we have an update in CMIP6, we ran UKSM 1.0. We have an updated version, UKSM 1.1, that was released about 1.5 years ago and documented in a paper by Jane Mulcahy and others in GMD. that has some improvements, and particularly improvements to the historical simulation. So we're thinking of, we also have that model running already with interactive ice sheets. So ICE here stands for Antarctic and Greenland ice sheets. And it does run in emission mode, in principle, both for CO2 and methane. We've run it with CO2, coupled CO2 emissions with UKSM 1.1 with interactive ice in anger already in a number of simulations. And we've also run a version with only the methane emissions, and we think combining the two will be relatively straightforward. So that would be our backup option for the fast track CMIP 7, where we would keep the UKSM2 development for what we call the science MIPS. Okay, so that's a plan that seems to be relatively supported. If things are delayed and everything can be done with UKSM2, then we would prefer that option. Just a couple of slides to finish with. So this is an example of the methane-driven model run in UKSM1, and it's in the full line, it's global mean surface methane concentration, and in the inset, it's the full atmosphere. Black is when we run in concentration mode, so that means prescribed from observations as best as they can be done for methane, and red is when we have an emission-driven model. So the model is deciding what stays in the atmosphere, what is taken up by wetlands, etc., and what the lifetime of methane is in the atmosphere. So there is an offset of order 20, I think you'll find this is of order 10 or 20%, to about 200 ppE by year 2000. The general feeling is this isn't too strong a bias. It's within the observation, it's within the uncertainty estimates of the natural and the anthropogenic emission estimates, and it may well be that the methane sink is a little bit too short as well in the atmosphere. So that's continued to be worked on, but we think this is usable. Last 2 minutes. So we've been testing a few things that are already going on. So we have a package of UKCA chemistry and aerosol developments that have gone in together that include things like improvements to stratospheric ozone. So in CMIP 6, this bottom right one, the UKSM model was a bit of an outlier in terms of the amount of stratospheric ozone. Developments at Cambridge, and I believe with people in Australia and New Zealand as well, have helped to, this blue line is an example from a test run, a nudge GAL9 atmosphere, which indicates, no, sorry, this is an atmosphere only, that indicates that there's a better simulation of ozone relative to the CMIP 6 multi-model, but also more importantly, the observations, which are these dashed line, diamond lines. And this red line is a nudged simulation of GAL9. So when you nudge the meteorology. There's a few other things that have gone in, Luhar lightning flash rate that goes in for NOx production, and a new development of ozone dry deposition. They're all in this package, as is the nitrate aerosol, prognostic nitrate aerosol, which amongst other things increases the AOD from the reference, which is red, to the two green runs, and increases the CDNC, and the ozone distribution changes, reduces the total column ozone. So we think these things are all mature, and we're pushing those through, and we believe these will be fully in the next system model. Fire is in there, and it's causing still some challenges. So initially when we had fire, this is looking at the Amazon tree cover. So it's the mean tree cover over the Amazon of broadleaf tropical evergreen. Black is what we had for UKSM 1.1. Blue is a UKSM 2 control without fire. Red is when we put fire on and let it interact with vegetation and the chemistry and the atmospheric composition, and we were getting a significant loss of vegetation. That may not be a surprise. There were some changes made to an ancillary file, basically, that controls the population, or gives you the population density and structure of the population density spatially. And with that there's an improvement or a lesser reduction in the loss of vegetation due to fire. And this looks like it's now relatively stable, at least. And there's a change in the distribution of fire, of vegetation, sorry, with the eastern Amazon, the relative increase, there's a relative increase in vegetation type in the eastern Amazon and a relative decrease to the present model in the western Amazon, Cerrado tree cover. And at least the people that work on the Amazon say this is an improvement. But this is still under development and is not yet ready to be fully tested. This is pretty much my last slide, just summarizing where we are with some of the other developments. So the ice sheets do work in an earlier UKSM 1.1 configuration, but there's a fair amount of work to make them technically work in a more user-friendly way, let's say. And one of the big things there is that the present model is running with NEMO 4.04. We do want to go to NEMO 4.2 because a lot of the technical work that was done for the ice sheets is now in there in the trunk, so we want to do that. The permafrost carbon work is important, I think, and it's progressing. The thermal acclimation is pretty well ready and is in what we call package testing, and the UKSM capability room with methane and CO2 is already there. So just summary then, the UKSM development, but this was put up yesterday for the CMIP7 discussion. So the core group team that developed the UKSM model and did a lot of our CMIP6 work, we have less resource this time round. So we were getting across, we had less resource, so that means the model development is going slower, and likely we will not have as many people for realizing our own CMIP7 contribution. We've switched the physical model from this emergent one to this central one because of the historical performance and the climate sensitivity. There is an amount of testing going on. We're hopeful to have a model by early 2026. This was for discussion yesterday in our meeting about the fast track model that I mentioned here again. It's a backup option, and we think it's an okay backup option. And then we will use the later UKSM2 model for most of the science. And with that, I will stop and take any questions that people would like to ask. Hope that was helpful.